So in these slides, we want to show how if you know the electric field in a certain region of space, and how can you get the potential at every point in space, using this infinitesimal difference in potential between 2 points that are infinitesimally close to each other. So this was the result we got a while ago in the previous file. If you have two nearby points and you want to get the potential at one point minus the potential at the other, and of course remember this whole thing is very small, the distance dr is very small, it's infinitesimal, but I just put it in big so you can see it. The difference in potential is equal to the value of the electric field at point A times the distance between the 2 points times cosine of the angle between them. This is what we had before. So what if we have a problem like this, where they put several charges, point charges, some are positive, some are negative, and they mapped out this electric field. Of course, the way they did it here is a bit strange. They put the electric field vectors to be the same length, and they indicate the strength of the electric field by the intensity. So when it's very white, then it's a large electric field. When it gets darker here, then it's a lower electric field. This is the way they did it here, because if they do it exactly, it will become very messy. So this is just the way they did it in this particular software. So what we want is, we know the electric field everywhere, and we want to get the potential everywhere. So we have to start at some point. So the idea is we can start at any point. So let's just take any arbitrary point. And we need to assign to that particular point a value of potential. And remember the previous files we mentioned that if you add a constant to the potential everywhere in space, it doesn't make a difference. That's why you can choose any value you want for the potential at that point. This particular software chose the value of the potential based on the fact that the potential is 0 at infinity, but you don't have to do that. You can choose any value of potential you want for the first point. So you can choose any point to start with, and you can choose any value of potential to start with. Then we know that if you move perpendicular to the electric field, when you put this circle here in the software, it shows you the exact electric field vector. So this red vector is the electric field vector. If you move perpendicular to the electric field we showed before, the potential doesn't change. So if I take the electric field and I go always perpendicular to it, you can see the electric field vectors here for this green contour. It's always perpendicular to the electric field, always, whenever you go around, it's always perpendicular. So you can map out this contour where the potential is the same value everywhere. It always has the same value. And this is based on the fact that we showed before for the infinitesimal circle. If you go 2 points where such that the displacement vector between them is 90 degrees with respect to the electric field, there's no potential difference between the 2 points. VA minus VB is 0. That means VA is equal to VB. And so as long as you move perpendicular to the electric field, the potential stays the same. And so when you do that, we mapped out this green contour. Every point on the green contour has potential 9.2 volts. Now, if you move to a point off the green contour in the direction of the electric field, we know that the potential will get smaller, because remember the electric field goes from high to low. So if you're going to a point in the direction of the electric field, as you see here, the potential gets smaller, it becomes 7.792. If you go to a point opposite the electric field, then the potential gets bigger. You can see here 10.44 for instance. And you can get what these values are based on knowing the electric field. Remember, if you go around the infinitesimal circle, you can get the value of the new value of the potential at that new point. And so then you can do the whole procedure again. Once you know the potential here is 10.44 volts, by taking the dot product between electric field and the displacement vector, then you can now map out every point where the potential is 10.44 volts, which is this other contour. It's always perpendicular to the electric field. And then you can keep on doing the same thing for the whole region of space. And so by that way you can find then the potential everywhere in this region. You can see here all these contours. This contour, the potential is minus 1.7 volts everywhere here. This contour, it's minus 0.76 volts, and so on. So you can, once you know the electric field everywhere, you can get the potential everywhere. And so the procedure, if you look back and we just make the procedure, outline the procedure, you start at one point, any point, and you put any value of potential. And we explained why in detail. And then you go perpendicular to the electric field and you map out the equipotential contour. And then you can go on either side of the equipotential contour and show how the potential gets bigger or smaller. And then you choose one side and go a certain distance away and get the new value of potential based on the infinitesimal circle equation. And then you continue the whole process and you map out the whole electric field, the whole potential.